perfect. So yeah, as Shane mentioned, I'm at the NASA Jet Propulsion Laboratory here in Pasadena, California. I'm the sampling science systems engineer. And so I get the great privilege of working at the interface between the science team and the engineering team as we plan out our activities coming up on the surface of Mars, especially to plan out our rock and soil sample collection campaigns that'll be coming up in the near future. So I'm here today to tell you a little bit about the project, where we are now, what we've seen, and really take you on a journey with us on what we've been doing, what we've been seeing on the Perseverance Rover. So Mars has fascinated us for a really long time. It's like a sister planet, a little bit smaller, a little bit colder, but it's a lot more like Earth than not. So what can we learn from Mars? And the answer is so much. We can learn about climate evolution, and we can learn about geological history that relates to our own planet. And with this mission, Mars 2020, we're striving to pursue for the very first time sample collection to return from another planet to our laboratories here on Earth to study, and to discover what we hope might be the potential biosignatures of past life on another planet. It doesn't get bigger and it doesn't get more exciting than this. And so how did we get there? So we launched on July 30th of 2020, and we arrived at Mars 6.5 months later on February 18th of this year, just a couple of months ago. We came screaming into Mars's atmosphere at about 12,500 miles an hour after flying almost 300 million miles through space over those 6.5 months. So this image just shows a depiction of the sequence of events of what we call our EDL, our entry, descent, and landing. So as I mentioned, we hit that upper atmosphere coming screaming in, and we've got to slow down. And we do that with a heat shield that eventually we jettison, and we release also a parachute that helps slow us down from supersonic to below the speed of sound. We use a radar on board in order to look for the ground and for potential hazards. And then we release the rover with its flying jetpack and do what's called the sky crane maneuver. So we avoid the hazards that we might otherwise not land safely with. And then we come down, we slow our descent with the rocket pack, we lower the rover down on cables, and as soon as its wheels down on Mars, that jetpack flies away and crashes never to be used again some distance away. But that's what we call the 7 minutes of terror. All of this has to happen without any joystick or control from Earth. Everything is pre-programmed in what we call an automated sequence. And so that magic is already done on Mars by the time we get the light signal back from Mars that it's all gone successfully. And hopefully, as many of you know, it did go successfully and it went really beautifully. So where are we? We're in Jezero crater. So this image depicts a map of the portion of Mars of where we landed. And we're going to Jezero crater because we think it's the site of an ancient lake and delta front on Mars from billions of years ago. So we're essentially following the trail of the water that we believe once flowed in this area and searching for, again, those potential biosignatures in the rocks themselves that might be left behind if there ever was life on Mars in this area. So here in this image, we depict a little bit more specifically in the blue, you can see where we landed. And you can see the blue circle, which is basically the landing ellipse. So that's the area in which we targeted. We could have landed anywhere within that ellipse. And so you can see off in the northwest or the top left of this image, the delta. So that's what we believe is actually the remnant of what was an ancient lake and flowing water. And right where we are, we're in the interface between some major geologic units that we're really excited with the science team to be studying. And we're already getting some amazing images, data, and observations along the way. But first, what I want to show you is a really fun video that, that NASA put together that gives you a little bit of an experience of if you were flying in the control room right along with us on this vehicle.
We are starting the straighten up and fly right maneuver where the spacecraft.
Sorry, I'm going to optimize the video and turn mine off.
Will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
So you're seeing the actual images from the rover as we descend on the parachute down towards Mars.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
And on the right of the screen, you can see the edge of the delta that I was showing before.
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
OVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So I've probably watched that dozens of times and it never gets old. That's really great. I hope you all enjoyed that as much as I did.
It's so much.
So what you really just saw is you saw a real first. You got to see, and I hope you'll go online and watch it again if you haven't seen it before, high resolution video of the entry, descent, and landing as seen from the rover looking down, as seen from the rover looking up at the sky crane descent stage as it flew away towards the end of the video, and of the sky crane itself looking down on the rover also as it separated and flew away. There is nothing like that feeling of actually seeing it through the eyes as if you were there piloting this spacecraft down to the surface of Mars and landing on Mars yourself. It honestly gives me chills, and what we're able to accomplish is nothing short of miraculous. So kudos to those on the entry, descent, and landing team who got us so safely to the surface. And so here we are. This is where we landed, and you can actually see an image here from orbit, one of our orbiters actually taking an image of the rover, and you can even see the light-toned scars left behind from the rocket nozzles as it descended and eventually flew away from the rover. It's really nothing short of spectacular. Okay, so let's talk a little bit about the science. So Mars, we know now, is a bit of a cold desert. And there's been some incredible climate change on Mars over the billions of years. We think, and we have strong evidence to believe, that Mars was once much more like Earth, with liquid water extensively on the surface and a thicker atmosphere that protected that water. And so for that reason, we can look to Mars and look in the past by studying some of the areas that seem to have had water present some long time ago, and study within the rocks and the soil and the regolith itself what clues might be left behind from what was going on at that time. So what might we look for? So here on Earth, we see things like the fossils that you see on the left from some 650 millions of years ago. But we also actually see here on Earth, even billions of years ago, evidence left behind in the rocks and the sediments of microbial life. And so these little trace remnants from the microbes that actually altered the sedimentary layers that were formed are not only 3.5 billion years old, but they're basically leaving behind what we call biosignatures. So these are the pieces of evidence that we can look for in the actual rocks or soil around it. And this is an example of a stromatolite. This is a formation that's produced when we have microbial mats that are growing, for example, on a muddy surface in shallow water. Again, I emphasize these are billions of years old here on Earth. And billions of years ago, we believe that Mars was much more like Earth and much more water rich on the surface. So here's an example of a stromatolite from Western Australia here on Earth. And so again, we'll look for the ancient physical and chemical structures within the rocks themselves to look for things that are billions of years old that we can sample with our instruments, and that we can collect samples from the rock and regolith soil to bring back potentially to Earth with our next missions. And deltas on Earth are a great place where we see all kinds of environments and signs of life. And the mud that buries organisms within these river deltas here on Earth really preserves them well. So this is what we call an area that has really high preservation potential for signs of life. And so we're looking at Jezero crater because of, again, that delta that we see, that ancient delta that may have preserved the signs that we'd be looking for if life ever existed in that area. And so again, here's where we are, in this case in the red star area showing our landing site. And we're looking towards the top of this image, we're looking northwest towards the delta. And so that fan shape towards the northwest is where we want to go from where we are. And we want to study not only the region where we landed, but the front of the delta, the interior of the delta, and eventually even beyond the crater rim. Now, this next image gives an illustration of what this area might have looked like billions of years ago, with the inlet channel towards the top of the image coming into this ancient lake, and then an outlet channel flowing out towards the right. Okay, so let's talk a little about the rover and then get into what we're seeing on Mars. So the Perseverance Rover is a really incredible system that we've put together with all sorts of great instrumentation and capabilities so that we can do this really intense mission. So we're going to be studying the geology of the rocks and soil. We're going to be studying the atmosphere. We're even carrying a subsurface radar that can penetrate below the ground to study the formations some meters below where we can actually rove. And we also have a very capable, what we call the sampling and caching system that allows us to be able to drill and acquire samples and process them inside the rover to store them and eventually deposit them on the surface, where we'll leave those samples in what we call cache depots for the future mission to potentially come pick up and return to Earth. So I won't go into all the details of all of these instruments, but suffice it to say we have some incredible capabilities to look at the chemical structure, the microstructures in very, very fine detail in the rocks, to abrade the surfaces away of the rocks that we might encounter and expose fresh surfaces in the front of the rocks below the weathering layer that's on top, or the dust cover, and then to be able to analyze them very carefully, but certainly not as carefully as we could if we were able to bring those samples back to these sophisticated labs that we have here on Earth. And that's really what we want to be able to do with this mission. So now that we're on Mars, let's take a look at what we've been doing and what we've been seeing. So here shows a few examples of some of the early activities where we were doing some commissioning and first-time motions on Mars. So on the top left, you actually see our first wheel wiggles, where we're actually moving the wheel steering actuators for the first time. On the lower left, you're seeing the robotic arm extended with the turret, or what we basically consider the hand of the rover, with its instruments and its drill mounted through the center. And so we're actually turning that wrist joint to make sure that everything's working, and also taking some really good pictures to make sure that once we landed, that everything actually looks like it's in the shape that we hope it to be. And so far, it's actually been really great. And then in the right side, you see our first wheel tracks on Mars. Again, it's like almost watching a baby's first steps, and it just feels incredible to see this rover not only working, but working so well, and going through these growing steps of commissioning to make sure that everything's working. And we're certainly on the move, making sure that we're heading towards the best science that we can accomplish in this mission. And then this image is one of our very first 360-degree panoramas taken by, in this case, this was the Mastcam Z instrument, where the Z stands for zoom. And so this is actually taking many images that are stitched together from 360 degrees all the way around the rover and checking out our landing site. And off in the distance, you can see zoomed in an appreciation of the detail for some of the sophisticated cameras that we have. And you can see this wind-carved rock in the distance that just shows some of the great detail that can be captured from our camera systems even far away. We call this one affectionately the harbor seal, because it looked in the distance like one of the harbor seals you might see in the San Francisco Bay. Okay, so now let's again put ourselves in context. Here we are at the White Arrow, and we're going to take a look at towards the top of this image, towards the delta, looking at the delta front and the crater rim in the next image. And so here you can see us looking in that direction, west-northwest, and you can see the delta front. That's the structure that's kind of closest to us, just past the sandy ripples in the front. And in the far distance, you actually see the crater rim. So you can actually see that higher sort of hilly structure. And yeah, that's the rim of the crater of Jezero itself. And you also see at the beginning of this pan, the inlet to the delta. So you can actually see how there's sort of a valley or a mouth, and that's what we consider the inlet entrance to what was once this ancient crater lake. And then in this image, you can see one of what we call the delta remnants. So this one's called Kodiak, off to the west of where we landed. And you can see some of the sedimentary layers and the weathering and even some boulder-sized structures embedded in this geological structure. And so you can imagine flowing water that once was raging in this area to erode this structure over geological time and to even move things possibly as large as boulders around. So this is going to be an incredible site to explore. And this is just an example of some of the great geologic diversity that we're seeing even from our own landing site. And speaking of diversity, so here's a few examples. So you can see great variety in the types of rocks, even from just meters away from where we landed. So towards the top left, we see some rocks that clearly look like they have some holes in them. Now, we don't know if this rock is sedimentary, meaning that it's been layered by water flowing over time and eventually water flowing through the rocks and dissolving minerals to create those holes. Or maybe it's volcanic in origin, and that gas bubbles that erupted from lava long ago solidified and produced similar looking features. On the top right, we see some low relief, light toned rocks, and we think that that's also probably weathering, possibly in the presence of water, but we're not sure. In the lower left, we also see some interesting, almost scaly type features in this dark toned rock. And this also looks reminiscent of some of the things that we see through water erosion here on Earth. But again, we're not sure, and we're just gearing up to study this in more detail. And then of course we see my favorite, the harbor seal, off in the top or bottom right again. So I should also spend some time talking about another great technology demonstration that flew with us to Mars. So the Ingenuity Helicopter. As many of you have hopefully heard, we've achieved the very first controlled powered flight on another planet. So this is really like a Wright brothers moment on Mars. And it's the first time that we've actually brought another moving vehicle with the first moving vehicle. So this helicopter was actually carried to Mars on the belly of the rover and deployed by the rover itself. And here's one of my favorite images. So this is a selfie that we take with the Perseverance Rover turret and the Watson camera on the turret, where it can actually outstretch its robotic arm, just like you were taking a selfie yourself on the surface of Mars. And so this is taken right after we had deployed the helicopter to the surface and just drove a little bit away, safely away from where we had deployed it. And you could see the Ingenuity helicopter off to the left. Again, this is just nothing short of spectacular, because we're seeing two moving vehicles, or vehicles capable of movement, right here in the same area, working together on the surface of Mars for the first time. And so here's a great video. So this is actually as seen from Perseverance and the cameras on board. We're seeing the helicopter actually fly. This is its third flight. You can see it take off after spinning up. It'll tilt towards the right. It'll fly away at just a couple meters per second, so probably about 4 or 5 miles an hour. And in this third flight, it's actually going about 50 meters, so a little over maybe 160, 170 feet away. And then it's going to, through its own navigation on board, where it's taking images of the surface and taking measurements with its inertial measurement unit, fly itself right back to where it started. So as I'm talking, of course, the helicopter's flown off screen and it's off some distance over to the right, and now it's flying back. And you can see with almost pinpoint landing, it's landing just within centimeters of where it had actually taken off after that reasonably long flight for this little helicopter that could. So this is just a technology demonstration, but it's a real amazing capability that we're seeing for the first time on another planet. And now the limits are endless as to how we might be able to use this technology in the future, either as a reconnaissance scout or perhaps instrumenting it with more capable instruments than just the cameras on board to actually do its own science mission in some future mission. And so in this image, you're seeing another fun first, where the Ingenuity helicopter during its flight is actually taking a picture of its local area, and you actually see the Perseverance rover over in the top left. Again, nothing short of miraculous to see something during powered flight and imaging the other rover that's just nearby. It's really, really awesome. So before I leave that, I'll mention that we've now finished 4 flights, the most recent of which is about a little over a football field of distance out and then back. And again, landing within, I think, within just a few feet of the original landing spot. And now what they're preparing is they're preparing for hopefully a 5th flight later this week that will take it further south from where it is now, and possibly to a new landing site. So instead of flying back to the same location that we know is safe, having now scouted out a little bit further ahead, possibly to land in a new location. And the rest of the mission for the helicopter will include what's considered now an operational demonstration that will actually try to test the capabilities of using a system like this to scout ahead for the rover. But the rover is now going to very soon transition into its own prime mission as this technology demonstration phase for the helicopter winds down. So what lies ahead of us? Sample collection. And so here you can see an example of the rover actually extending its robotic arm and the coring drill coming down on some rock surface to be able to collect a core sample in this case. And what you see on the left is you see an illustration of one of our sample tubes, and we carry 43 of these on board the Perseverance rover. And you can see an example from ground testing of one of the rock cores that we collect. These are about 13 millimeters, just a little over a centimeter in diameter, and anywhere up to about 70 millimeters in length, or 7 centimeters. And we're going to collect up to 38 of these over the course of the mission, and then 5 sample tubes also contain what we call witness samples that allow us to also check for any background contamination during any of the sample collection processes. So now let me play this animation, and I'll turn off my video again. Sorry, give me a second. Optimizing here. end of the robotic arm is the coring drill. In this case, you see us loading our stabilizers against the rock, drilling and coring down into the rock itself to obtain that sample that we want to collect. Crafting back away. And now we dock the image in the belly of the rover, what we call the adaptive tracking assembly, where we transfer the bit from the sample rover down into the belly, and we have a small robotic arm that we actually use to manipulate the sample tube inside the rover. So we'll go through measuring the volume of the sample, sealing the sample tube hermetically, imaging the sample, and moving the tube ultimately into storage before we drive to where we're going to actually drop off the samples at some point later in the mission. So after we go ready for the next one. So there's a series of amazing events that have to happen to make this all work. And why are we collecting these samples? Again, we hope to bring them home one day and be able to study them in much more detail in the sophisticated labs here on Earth across the world. But to do that, we're going to have to do a mission called Mars Sample Return as a campaign of several missions that we hope will be pursued in the not too distant future. So that begins with our Mars 2020 mission, collecting these samples, as I mentioned, and it would continue with a lander that then would deploy a small rover to basically go fetch those samples that we leave behind. We would have a small little rocket on board that we would transfer the sample canister into what we call an orbiting sample container and launch them into orbit around Mars. And there would be yet another spacecraft, an orbiting spacecraft that would actually go rendezvous and capture the orbiting sample container. And then that spacecraft would return to Earth to deploy a small little entry vehicle that would land on Earth with the samples safely, all very carefully contained to make sure that everything is completely protected from any possible contamination both ways. And so that's a string of an amazing set of events that needs to happen, but it's also an important thing, not just for science, but also for enabling future missions, hopefully one day for humans as well. So we've gone to other planets, and in this case on Mars, we've been to the surface of Mars several times, but we've never come back. We've never gone to another planet and then brought that sample back. And in this case, we're going to bring literally scientific samples, but one day we hope to be able to send humans and let them explore and also come back safely. And so the technologies that are used for all of this are also important to show and demonstrate during the courses of these missions so that we can enable that future. Okay, so back to the science of Mars 2020. Really, we've just begun. The scientific journey is just ahead of us. We're finishing up the commissioning phases for a lot of the sophisticated capabilities on the rover. And we've already been doing some great studies, but with a limited set of some of the instruments that we have on board. We're going to be moving, and we're going to be moving much more significantly than we have recently, as we've been mostly bound to the near vicinity of where we landed, partly because we wanted to do this helicopter phase in a known and safe area. And we're going to be roving to the south and towards the west of us, and we'll make our way down there to explore some different areas that we have seen from afar. And then eventually we're going to make our way steadily up and toward the delta, towards the west-northwest. So we'll probably be collecting samples along the way, and then certainly on the delta itself and the sedimentary layers that we might see there. Eventually we'll climb up and out of the delta and likely make our way out of the crater rim towards the west. And so this series of events is going to be spanning, several years. It's not something that happens just overnight or in a few weeks. And so it really is an odyssey of a journey that we're laying ahead for us. And so here are just a couple example views of what we're seeing from our landing site and giving us another sense of what's ahead. So on the top, you can actually see a view towards the east, and this has been an area that we've been exploring just a little bit away from our landing site as we've been in this helicopter phase and studying some of the rocks and the outcrops that we see in the local vicinity. And then looking southwest from our landing site, this gives us a little bit of a view of where we're going to be going next in the next coming month or two. And I couldn't finish this talk without really talking about the people. We've not only had the hundreds that you see shown in this image, but we have partners across NASA, across industry, across academia, and certainly even our international partners and other space agencies, including Europe, that have made this all possible. Everything from the business team to the technicians, to the engineers, to the scientists, and of course the public that enables all of this makes it possible. But teamwork is at the heart of it. And so not only is that an essence of how we get it done, but it's also what makes the journey so much fun, working with all these great people. And so again, the adventure's just begun. I want you all to hopefully get excited as I am about all of this and keep exploring with us. So check us out online at mars.nasa.gov/perseverance or /Mars 2020, and follow us online on Twitter and Facebook at NASA Persevere. And again, I want to thank you all for your time, and I'll hand it back to Shane and hopefully can answer some questions.
All right, let me unmute myself here. Well, thank you so much, Robert. I have a privilege here. I got a special preview of that presentation a little bit early, so I knew I was pretty excited to see some of those videos and pictures that you had shared. Yeah, just incredible stuff. So I think we do have a couple questions here. I want to get started with a fun one. This is from Nina and Maria, who are some preschool students at the Science Center here. So they have written down a question here for Mr. Robert, and they want to know, will NASA ever make rovers that can come back home to Earth after being sent to Mars?
That's an interesting question. So right now, we're not planning to bring the rovers back because it's such a great asset to have this on the surface of Mars, right? And just like the previous rovers, we're probably going to keep using them for as long as they remain viable to keep studying for scientific exploration, right? But as I mentioned earlier, what we are certainly looking at doing is we're going to be returning the samples, and we're hopefully laying the groundwork for what will become enabling the future with humans to Mars. So hopefully some of those preschool and other kids you're talking to, Shane, will be some of the first footsteps on Mars one day.
Yeah, that's such an exciting way to think about things. Well, thank you, Nina and Maria, for a great question. That was very good. I have a question here from Dan. Wants to know, is it correct that if the mission is extended beyond its prime mission, that the rover will then be somewhat close to one of the other candidate landing sites?
Yeah, so yeah, if extended mission does get approved, then almost assuredly we'll be making our way out of the crater. And so we're going to be heading west, as I mentioned, out of the delta and out of sort of that inlet channel. And so, yeah, there's much to explore off to the west. So once we're out of Jezero crater, as exciting as the potential science is there, we've got a whole other region to explore. So if Perseverance's systems, are still in good working order, even after we finish the prime mission and leave behind the potential sample caches for the future missions, we've got a great suite of instruments on board that we could still study in situ, meaning there on Mars, locally, a lot of the great geology and other regions that we might see towards the west. So yeah, great question.
Cool. Well, thank you everyone who's shared questions so far. If you have any questions here, add them to the chat. I have one here from Kay. She wants to know, what energy source does the rover use to operate?
Yeah, that's a really good question. I didn't touch on how it all works, right? But yeah, so this rover, much like the Curiosity rover that landed in 2012 and is still going in Gale Crater on, well, a few thousand miles away. So we have what's called a radioisotope thermoelectric generator, an RTG. It's basically a nuclear battery, so it actually uses the radioisotope decay of plutonium in a very safe and controlled way to generate heat. And then those that heat through thermoelectrics actually generates electricity, as well as it generates additional heat that we can use on board the rover itself to keep things warm in such a cold environment like Mars. It gets really cold in the Martian nights, especially in the winter. So with that system, what's great about that is that we can actually operate almost any time of day. Depending on the planning cycle, we can actually do a lot of activities at night that might otherwise be limited if we were only restrained to solar power alone, right? And so it gives us a lot of operational flexibility, and again, has heritage to the previous Curiosity rover design. Again, that's a good example of where we work with some great partners, in this case with the Department of Energy, to help us, create such a system and have it available for a select few space missions.
Well, thanks for digging in on that a little bit more. Maddie wants to know, while roving, does Perseverance take samples periodically or in strategic locations?
Yeah, that's also a great question. The answer is both. So we have planned strategically where we think some of the notional areas to sample are going to be most compelling from a science perspective and from an engineering capability perspective over the course of the mission. But now that we're on the ground, of course, we're learning new things every day, every week. And I can assure you the science team is really excited about getting our sampling capabilities online here in the next month or two, so that we can actually get to sampling nearby where we've already landed. So we've got a great plan for what's going to be roughly happening over the next month or two, and we're going to possibly be collecting several samples within the next following few months once the system comes online in the early summer.
Excellent. Okay, so it looks like a question on sample retrieval or sample return. So are you saying that samples will not come back to Earth until we are able to land people there and they can bring them back?
No, quite the opposite. So what we want to do is we want to be able to do it robotically first. For a couple of reasons. One is we want to be able to use the robotic systems in order to bring those samples back safely, more cost effectively, and to actually demonstrate the technologies that we need for the human round trip capabilities, right? Albeit at a smaller scale. Additionally, we're really very, very careful in this mission scientifically about what we consider for contamination control. And so you could imagine the last thing we want to do is bring Earth bugs or microbes, from Earth to Mars, and then drop them on the ground, sample them, bring them back to Earth and say, hey, we found life, but it actually just turns out it was Earth life we brought with us. So we've been really, really careful about ensuring that things are super, super clean. And that's a really important part of the mission. And so that needs to happen all the way round trip, right? So ironically, when eventually we get to sending humans out there, we're inherently going to be somewhat contaminating the surface. Humans have to breathe, they have to exhale, and they have to, eat and all those things. And eventually some of that stuff has to actually get left behind, either in the Martian atmosphere or on the ground. Humans will be able to do some incredible science, but first we want to be able to bring these samples back as safely as possible and enable that future for the humans.
Cool. Are there any plans to go to Venus? This is a question from a Science Center preschool alumni. So any plans to go to Venus? I'm interested as well.
Yeah, so the answer is the whole solar system is wide open. We actually have some what we call competed proposals at NASA that are being evaluated right now, some of which include some Venus mission concepts. I'm not personally as familiar and involved in those, so I can't really speak to the details, but I can absolutely say that Venus is another terrestrial Earth-like planet that we're very interested in, and certainly very different than Earth, right? More of a greenhouse gases run amok kind of environment there, right? And it presents its own very, very different challenges than being able to study the surface of Mars. In some ways, it's easier to send a spacecraft there and to study, at least from orbit. But in a lot of ways, it's even harder to be able to land and survive on the surface. So sample return from Venus may be a one-day thing, but it's definitely going to be a little bit farther off in the future. But yeah, there's some great concepts there for studying Venus along with Mars and the other terrestrial planets so that we can really understand Earth as a system, within this family of different planets of ours.
Cool. Yeah, that was an interesting question. I think that speaks to the nature of this mission. Just what it does is it just gets you thinking of, okay, what else? What else can we do? What's next? So,
That's right.
uh, yeah, that's really cool. All right, I like this question. What kind of harsh environment testing does the rover have to go through before a mission?
Oh boy, that's a really good question. So this is why this takes so long. Um, we started working on the early concept development back in 2012 and 2013 on this mission. And so you can see here we are some, 8+ years later, finally operating on the surface. And there's a reason for that, right? We go through some really detailed design work and careful, studies and integration of that design, but then we build it. And that's an interesting challenge in and of itself. And we assemble it and then we test. So we go through everything from simulating the launch and the landing environment through, massive vibration tests, where we literally shake, rattle, and roll the system and make sure it survives all the loads that it might experience at launch and landing. We put it through what we call a system thermal test, where we cycle it, like the day and night hot and cold cycles for days on Mars, and make sure that the systems are actually able to operate as designed over, hundreds of degrees of temperature variation. It's just really tremendous what, the Mars day cycle can be. And of course, to be able to survive the vacuum of space and the low pressure of the very thin atmosphere of Mars. And all of that has to work before we can actually say, yep, we certify that this spacecraft is ready to launch. So yeah, a big part of the tail end of the mission before we launch is really just testing at every level, from literally the nuts and bolts of the hardware to the electronics to the full up vehicle once it's all fully assembled at the full flight system level. And yeah, we get one shot to do this, right? And it has to work. And that's part of the miracle and the fun of a job like this is realizing, yeah, there's no mechanic on Mars. There's no, charging station in deep space, at least not yet. And so we got to bring everything with us that we need. And we've got to actually make sure that we're designing it and testing it so that it can really handle all the extremes. And when it works, it looks like magic, right? You see these videos like that entry, descent, and landing video, and it just looks like everything's going off like almost like a movie, right? But what that really shows you is that shows you the thousands of, hours of work that hundreds of people have put into all of this to design it and test it to make sure that it works just right. And when it doesn't work so well, you know it.
Yeah, that's the truth. I think that's just a really good way to kind of wrap things up here. I do have one more question though. Oh yeah, this is a good question. Thanks, Dan. Are many or most of you still working remotely?
Yeah, absolutely. So unfortunately, yeah, we're all in these strange times, and frankly, this mission was a first in a lot of ways, having to experience going through the final preparations before launch, and then flying, from Earth to Mars, and of course now early operations on the surface, all in these COVID pandemic times. But I'll say we've learned a lot. We've, done, I think, an impressively good job of being able to work in a hybrid mode where we've got a small team that works, on site, especially at JPL, for our operations center. And then a large number of us, especially in the science team, that are distributed all across the world, frankly, and continue to support remotely. I myself, work more often remotely from home than I do going into the lab to do what I need to do. But it really just depends on what the activities or the planning activities are. And so obviously we're, continuing to evolve with all of that as things get a little bit better with the pandemic. But yeah, we've had to learn to deal with lots of technical challenges, but also lots of unexpected challenges with working remotely. But I'll say it's definitely taught us a lot of really good things and some things that we'll be able to carry forward into, future operations as well.
Yeah, I bet that was quite the transition to a mission, to put on a mission like this from a remote working. That would be quite quite the task, but yeah, it's all the more impressive that everything got pulled off and went so well. So yeah, well, I want to thank you again, Robert, for joining us. I think kind of brings us to the conclusion of our presentation here. So I appreciate your time so much. I know how busy you are. Good reason. I mean, just to be a part of something like this must be incredibly exciting, but a lot of hard work. So I really appreciate you giving us some time here.
Yeah, thank you, Shane, and thank you to everybody who's participated in this or who might be watching it later. I just want to again say, you know, a colleague once said to me, we're in the business of inspiration, and I truly believe that, right? I think especially during, you know, the difficult past year that we've all had, to have an opportunity to you know, share just a really cool experience and journey, you know, with everybody, and just feel good about that is really important. And again, we're just beginning, so please, you know, follow along. And for those, you know, parents out there with young kids or young kids who might be participating right now, let me just tell you, you know, you might be some of the first people that that actually get to work on these samples for the first time when they come back from Mars, right, in the not too distant future. And so, yeah, pay attention in your science and math classes and everything, right, and help us get this job done, right?
Yep. Go to Science Center camps too. That'd be a good thing.
Do that.
All right. Well, thank you so much, Robert, and thanks everyone for participating this evening. I hope you enjoyed the presentation. On behalf of the Science Center of Iowa, thank you for attending this session of Café Sci. I'm going to put a slide up here at the conclusion with a link to a survey. If you could take 5 minutes and fill that out for us, we would really appreciate it. There's even space for you to share any ideas you have for future topics you'd like to see covered by Café Sci here as well. So have a great rest of your evening, everyone, and a great rest of your week. And I hope to see you all real soon.
All right. Thanks, everybody. Bye.